So, today we will continue with photoacoustic techniques for maybe tomography applications. Okay, photoacoustic tomography. So, as yesterday, we were talking about the photoacoustic signal which is generated by optical pulse, most of the time lasers. So, the laser pulse interacting with the tissue, and the tissue absorbs the part of this light, right. So, the optical pulse or the laser wavelength should approximately match with the absorption band, then the efficiency of photoacoustic generation will be good enough. And then the pressure wave which is developed produces the acoustic signal. And so, it is now the approach what you can see here is similar to what we were talking about photoacoustic spectroscopy in order to measure the absorption, means basically concentration of molecules, etc. Now, it is slightly different, right. We are trying to observe some the tissue characteristics indirectly based on photoacoustic signal, but the more or less the technique is very similar. So, modulated laser beam, now in terms of pulse width maybe short enough, which is absorbed by the tissue, and so that is a local absorption. Now, we will see in the next week that this light absorption may also result in some radiative relaxations, okay, maybe fluorescence, maybe phosphorescence, etc. At present we are not interested in this. Now, whatever this are radiative relaxations will be in the electromagnetic wave, this part, and when they are radiated in the tissue samples, then due to scattering, etc., they get lost. So, it is not very easy to pick up. And however, acoustic waves which are generated due to the local temperature increase, adiabatic expansion, okay, resulting in which is resulted due to the local temperature increase, and then pressure wave generation, and this pressure wave is acting as an it produces some impulsive force to produce acoustic resonance, okay. So, and this acoustic resonance is captured using microphones, okay, or some other acoustic detectors. Now, the microphones may be based on capacitive based approach, or it can be a piezo electric sensor in this case, okay. So, this sensors they will pick up acoustic waves with a frequency of the order of megahertz, okay, or sub kilohertz, sub megahertz, okay, or megahertz, and this modulated photoacoustic signal is used for imaging purpose. So, so this is the basic, and as what it captures is, let us say in beneath skin or within the body, any particular position, let us say it is a thyroid gland, etc., located not directly exposed, is not it, but the laser beam can propagate through this skin tissues and can interact with this thyroid gland, okay. Depending upon the absorption, the thermal waves generated are captured. Now, we can also capture infrared approach in order to measure the temperature change, okay, one approach. However, photoacoustic cell can capture the photoacoustic signal, which is much better in terms of less scattering and right due to tissue samples etc., and it can be efficiently captured. Now, this scattering what is captured, if we try to image it from different positions, we will be able to even capture the location as well as various other features surrounding those tissues. At the same time, it is also possible to capture even the time resolved pressure. So, let us say we send a laser pulse which is nanosecond order as compared to the let us say DC light source or laser diodes with a high frequency. We can use it as a modulated source or a nanosecond pulse laser. If we send, we can see that with single pulse, when acoustic waves are generated due to the pressure change, adiabatic expansion and pressure which is is increased in this confined region, that pressure increase and it will decay, it will decay with time, because as the pulse ceases, the pressure pulse will also start decreasing. So, we can also obtain time resolved pressure, this relaxation characteristics etc. Based on that also we may be able to characterize the tissue, this characteristics. If the tissue is hard or soft, depending upon that the pressure change, decrease in pressure change or the relaxations pressure you can see the pressure plot characteristics with respect time will be different. So, those aspects can also be captured. Now, this pressure which is generated is given by this pressure rise is given by parameter which is beta, coefficient of thermal expansion and isothermal compressibility of the tissue and T is the temperature at that position. So, when we are sending the laser pulse and so that is which is pulse width maybe of the order of 6 to 10 nanosecond, much shorter than the relaxation time. What is the meaning of? There are two aspects related to relaxation time. One is thermal relaxation. Thermal relaxation comes into picture. Now, this thermal relaxation is given by so basically when laser interacts with this tissue sample, the sample absorbs that heat, it get diffused, the thermal heat will get diffused, and this depth of diffusion sorry, the depth of diffusion, let us say it is d, is given by alpha this is thermal diffusion, this is related to thermal diffusion coefficient, coefficient into tau. So, tau indirectly in this case is related to thermal relaxation. So, tau is nothing but d square by alpha thermal diffusion. Now, this alpha thermal diffusion is nothing but conductivity of this thermal conductivity of that, it is basically thermal diffusion represented by thermal conductivity of the material divided by density into specific heat. So, divided by this space. So, K is thermal conductivity. Rho is density, tissue density, and C is the specific heat. So, this parameter alpha and that the thermal heat, right, which is diffused in the tissue sample, these two aspects will determine indirectly they represent thermal relaxation. Okay. So, the thermal relaxation in fact is defined by when the temperature right of this tissue reduces by whatever is the increase, right, from there it reduces by 50%. So, approximately that much time taken is known as the thermal relaxation time, and it can be estimated using this, right, approximation. Okay. And there is one more parameter which is stress relaxation time. Okay. Stress relaxation time. So, this stress relaxation time, okay, tau s, is given by this heated region, okay, d, divided by the sound velocity, okay, sound speed. Okay. Okay, this is d is the heated region. And this parameter is generally, right, this tau s will be microsecond order or sub microsecond order. Thermal relaxation may be order of microsecond to millisecond order, we will see estimate approximately, and the laser pulse which is used, right, should be shorter than this. Okay. Otherwise what will happen, it will be a cumulative effect of the laser pulse interacting with the tissue, simultaneously relaxation is taking place, and right, it will end up with of course, as the pulse width is large enough, thermal diffusion will also be large in that case. So, the nearby tissues will also get affected by due to the temperature increase, right. So, generally the laser pulse width or modulating frequency should be, right, such that the pulse width of the laser interaction should be short enough, okay, or the pulse width should be short. So, let's say just to give one example, what is the time scale with which we are operating when we talk about thermal relaxation or thermal stress relaxation. One example, so this I have taken from the book only. So, let us say let us say sample which is the tissue sample which is getting heated, okay, the order of 1 millimeter, okay, and for right, for our right body tissue sample using the parameters thermal conductivity, specific heat, etc., the alpha of thermal diffusion is approximately 0.13 millimeter square per second, okay, it is this, okay. So, this will give us the thermal relaxation time of the order of which is d square by alpha, right, thermal diffusion coefficient alpha, then it is right 1 divided by 0.1. So, approximately 1 millimeter square, no, d square divided by 0.13, unit is millimeter square by second. So, it is around 7 point, right, 7 to 8, 7.7 second, okay, approximately. So, this is the right when single pulse interacts with, right, material, and if the heat diffusion is of the order of 1 millimeter in the tissue, we will see that the thermal diffusion time, okay, or relaxation time is approximately very long, right, very long, 7 second or so. while stress relaxation will use, if we can estimate. Now stress relaxation is given by d divided by speed of sound in tissue, which is of the order of 1480 or 1500, right, means approximately near, right, water we can say. So 1.48 millimeter per microsecond, okay, and d is of course 1 millimeter in the from the previous, right, just example. So we can this is around 0.68 microsecond, okay, tau s. So thermal relaxation time is of the order of microsecond, okay, on this. So the laser pulse width, right, shorter than this is, right, is better. So it will be, of course it can indicate to you, right, that the laser pulse width will be much shorter than this, few nanoseconds, etc., if we are using a pulsed laser. If we are using let us say diode laser, etc., which is their CW, continuous wave. So we will have to apply modulating, right, output. So in that case the modulating frequency will be such that the it should be lesser than the time, right, between each pulse, modulating this pulse should be less than this, isn't it, approximately. So it will be in terms of kilohertz, few hundred kilohertz or megahertz, correct, so as to induce the thermal heating effect. Is it okay? Is it fine? So this is in general, it gives us idea about what should be the type of, right, this pulse, etc. Now what is the temperature that you expect to increase? No, I am talking about, okay, temperature increase. Do you expect the temperature to increase by how many? Let us say laser interacts and we want to observe such acoustic signal. So what do you expect? Just, of course you have not estimated, right, but just what you can imagine, maybe if 100 Kelvin increase, millikelvin, etc., right, it will be, why, if it is more than few kelvins or 10 Kelvin increase in temperature, the tissue will get charred off, right. Of course we will see that temperature ranges, etc., when we talk about therapeutic applications, okay, but at present it is when we estimate using this. So again here just from the experimental some examples, what is the approximate temperature increase? So how do we estimate? So if we can estimate the total heat which is input, right, generated, how do we estimate the heat generated? If we know the intensity, right, and we know the absorption coefficient, it will help us how much amount of, right, power is being absorbed, right, intensity, and then we make use of we will assume that no diffusion is taking place, short pulse, no, it is 5 to 6 nanosecond pulse width is short, within that period of time the heat is not getting diffused in the tissue, let us assume. So in that region where laser is interacting, within 5 to 6 nanosecond where heat is not diffusing out, the temperature increase will be indirectly can be given by increase in the internal energy, m mass into specific heat into delta temperature rise, okay. So we, by assuming such, if I allow heat to diffuse when laser pulse is interacting, if the laser pulse is long enough, the heat will start diffusing, okay. So in that case what will happen, right, not only temperature increase but the conductivity will also come into picture, okay. So that part has to be kept in mind. So in, let us say the laser fluence, okay, we are using a short pulse laser, okay, short pulse laser, okay. So when we when we write short pulse laser, pulse width is approximately 5 to 10 nanosecond, okay, 5 to 6 or 10 nanosecond, okay, short pulse laser, okay, and fluence is given as 12 millijoule per centimeter square, okay, and the absorption coefficient of the tissue corresponding to the wavelength, let us say the wavelength of this laser beam is 1064 nanometer, okay, laser beam. So, correspondingly the absorption coefficient of the tissue is 0.1 per centimeter, okay, per centimeter, okay. So, right, so this is given. Now, density of tissue rho is 1 gram per centimeter cube approximately, of course, CV. So, this basically right, it is a soft tissue. So, based on that CV is available from the data, okay, 400 millijoule per gram Kelvin, okay, that is the unit. So, we know fluence right, and mu A absorption coefficient will give us amount of energy which is absorbed by the tissue sample, and as I told you, mass into specific heat into temperature difference is equated to that heat which is absorbed or energy which is absorbed. So, if we use that formulation, okay, so it is basically mu A into H is the H is nothing but the fluence, let us say, is the amount of energy which is absorbed, is compared with rho CV into temperature rise, okay, delta T, temperature rise, okay. So, using this formulation we can estimate mu A is 0.1 centimeter inverse, H is 12 millijoule per centimeter square, rho is 1 gram per centimeter cube, CV is 4000, right, millijoule per gram per Kelvin. So, which will give us delta T value which is increase is 0.3 millikelvin, okay, it is very small, okay, temperature rise. So, it is not going to damage the tissue, it is not going to damage the tissue, right. Tissue damage will come into picture right in the particularly when the temperature rise is more than few kelvins, okay, 1 5 10 Kelvin, then temperature rise is significant enough for tissue to start, right, getting burnt, right. That is why we know when we increase the, right, hot water temperature beyond 45 degrees centigrade, right, means temperature difference is only 10 degrees centigrade, right, our tissue will start burning, correct. It is similar here also, correct. So, its energy which is absorbed will end up with temperature rise is of this level, okay, very small level, okay. Question, no problem. So, now this will, what it will do, it will produce a pressure wave, right, because of the confinement of the tissue right within that right tissue structure. So, that pressure is given by this parameter, okay, BT sorry, by sorry, okay, I should kappa, okay, okay, kappa. So, beta is nothing but okay. So, the P0 is the pressure rise, okay, and I will tell you what is beta is related to thermal expansion, okay. Okay, that is that basically it is a coefficient of thermal expansion, okay, because of the temperature rise there is some thermal expansion, okay, and that is given by this beta parameter, okay, and which is for right, the tissue, it is approximately 4 into 10 raised to minus 4 per Kelvin, okay. Okay. Thermal expansion coefficient, okay, per Kelvin, and kappa is isothermal compressibility. So, in a confined region, the tissue which is surrounded, no, that right, that confinement induces compressibility, and it is approximately 5 into 10 raised to minus 10 Pascal. Okay. So, if we substitute all these values and temperature rise is 0.3 millikelvin, P 0 will be of the order of, I think it is of the order of 2.4 into 10 raised to 2 Pascal, okay, or 2.4 millibar, okay. See, right, 100 kilopascal is 1 atmosphere, okay, 1 so much smaller, right, the pressure increase is much smaller, but this is sufficient enough, right, to generate the acoustic waves, right, and that those acoustic waves are captured, okay. So, so if we try to see those aspect, right, what we do, we are using ultrasound, right, detector, right, ultrasonic detector, which is a piezoelectric detector, okay. So, what will it do? It will pick up this acoustic signal which is generated below some, right, some depth below the tissue surface, where laser is interacted with the tissue, it has produced some temperature change, and that is producing this, okay. So, this is the photoacoustic mechanism as far as right, for tissue interaction is concerned, okay. And there is a coupling medium, because when detector is placed on the tissue, if there is an air gap, it will produce some because air is not a good conductor, right, of in the sense reflection, impedance mismatch will come into picture, okay. So, so it is now if we put multiple such detectors, okay, or move the detector, right, right, in a linear circular way or linear way, we will be able to capture the signal from different directions, acoustic signals or ultrasound waves which are generated due to the laser interacting with the tissue, okay. So, it is basically local heating generates the acoustic wave, and those acoustic waves are captured, okay. So, this is the way we can make use of such approaches in order to imagine some of those, right, tissue characteristics, okay. Now, this is of course, I already explained to you, pulse width is a short pulse laser comes, interacts with, this is the, let us say, tissue, right, structure, it interacts and heating takes place, right, heating takes place, and of course, part of that light may get transmitted also, some part which is not getting absorbed, small part may get so the intensity of course will reduce, and it may not be so large to generate, right, very high, very means significant temperature rise, etc. It will be very small, because most of the part of this input laser is being absorbed by the absorber, which is nothing but a tissue, right, structure, and it will generate acoustic waves, and if we have a detector system surrounding this, we will be able to capture the signal. So, and that can be analyzed in order to, right, capture the information. Is it okay? So, so basically this part is useful for I will just go this, all these things so it is useful. So, there the right in right, so this technique has evolved first with photoacoustic imaging modalities, right, and so 2000 right onwards such photoacoustic techniques are being developed. So, lots of improvements have of course taken place, but you can see that basically the idea is to capture this right acoustic signal from different direction. So, you can have a transducer which rotates all around, correct, right. As each single pulse you will obtain single such photoacoustic signal, and then rotate this to capture the whole right imaging part right at that particular height, and then you can vary the height etc., so as to right allow even some up to some extent even the right depth information. So, this is the one idea. So, it is based on single element ultrasonic transducer rotated all around. It is also possible to capture right using an array of transducer and capture the signal. In fact, this has been right also been taken right, it is possible to observe. So, what are we observing? So, we can observe if there is any tumor in this right tissue etc. So, that tumor will have different characteristics than the surrounding tissues. So, the thermal relaxation as well as the stress relaxation will be different over and above because of the different tissue characteristics. The acoustic frequency with the acoustic sound which is generated with frequency will get shifted by small amount, okay, depending upon the material characteristics. Okay. So, if it is not only imaging what we want to do, we want to capture the differentiation between different tissue structures within that right imaging area. Then for that purpose we need something more, not only to acquire this signal as an acoustic amplitude, photoacoustic amplitude, but to capture some spectral information, so that ultrasound spectral information can provide us something more about the tissue characteristics. So, okay. So, that aspects started coming from 2009, 2010. Many research groups not only wanted to acquire the imaging part also, right, but also to distinguish different tissue samples etc. Okay. So, in fact, some research groups have also combined this acoustic signal this laser pulse matching with the let us say the blood absorption wavelength. Okay. So, you can even you can take the image of the vessels through which the blood is going through, okay. Because if I match my absorption wavelength to 600 nanometer, we know oxyhemoglobin and hemoglobin has a very good absorption extinction. So, 500 nanometer Nd:YAG laser second harmonic frequency matches with good absorption of blood sample. So, when we use that, we will be able to see the acoustic signal generated due to very large signal generated when the blood is present, or depending upon that we can even imagine the area surrounding that blood also. We can even find out blood clot if that is present in this. Okay. So, these techniques are being used to capture or being developed, I should say, right. It is still has right clinical applications are just starting up with various ways. However, this technique can allow us to image right the blood clots or blood flow, not only blood flow, but also the vasculature, how the blood is right is flowing all around can be captured right by using two-dimensional imaging modality, we can capture this information. So, that is one more such example. In fact, as I told you, so blood, melanin, endogenous absorbers are used, or lymphatic fluid or contrast agents are also used to allow more absorption of the light and then capture, okay, the various light characteristics related to tissue structures, etc. Okay. So, that is one, and just last this part. So, spectral response, right, if it can be captured, okay, it is not only capturing the photoacoustic signal and taking the image out, bringing out the image, but now distinguish different tissue structures. Okay. So, approach is very similar. Okay. So, laser interacts with the tissue, and a sensor right over here right detects the acoustic signal which is generated. Okay. Now, this acoustic signal is captured with the help of digital storage oscilloscope. It can be the tissue, it can be a solid tissue, or it can be a maybe a liquid sample, etc. These are experimental setup, but what they have observed that let us say the acoustic signal which is generated in time frame is captured using spectrum digital oscilloscope with the photoacoustic transducer, sorry, acoustic transducer, it is captured, and then through Fourier transform we will be able to convert this signal into the frequency range. And if we see the frequency distribution, it is of the order of few megahertz or sometimes kilohertz, a few hundreds of kilohertz, etc., depending upon the type of tissues, etc. This is just a simulated signal, just to show you how. However, let us say samples, we take samples with different densities. Okay, we take. So, one sample, it is an lab experiment. Okay, the output is not actual, but the lab experiment. If we take a sample which is having a density 0.025 gram per milliliter and the other one 0.075 gram, depending upon the density of the sample, the frequency response is different, is being captured. Okay. So, this is photoacoustic spectral response measurement. Okay. Not only photoacoustic signal being captured, but the frequency response is derived, estimated, and then it can give you. So, this is I have taken from some of course reference I will add this. So, morning only I updated this. So, this is about thyroid gland. Of course, this experiment is not performed on the human being, but it is extracted thyroid gland. Okay, and that thyroid gland in some region has some maybe carcinogenic tumor or tissues, etc. So, the thyroid has different regions, and laser 532 nanometer green laser is used to interact with such tissue samples. So, different parts of this tissues are being irradiated with laser and acoustic signal is observed. What was observed in terms of frequency distribution of this photoacoustic signal, if it is let us say normal, let us say approximately normal tissue, you can see that the curve is approximately so this is maybe black color or blue color, blue color or black color, approximately. How sorry, yeah, but in case of carcinogenic tissue. So, basically thyroid, this gland with tissue with carcinogenic, right, or malignant tissue. The characteristic is slightly different, as it is shown by red color photoacoustic signal, or of course frequency spectrum of that signal, or green color, right. So, it can be distinguished, right, normal tissue and some the tissue structures can be distinguished using this approach. Okay. So, it can also be used to distinguish blood samples and clotting region as well. Okay. So, if it is a blood clot, the spectrum is much broader, frequency shift is also observed. Okay. So, how right, how this is are all experimental outcomes, it is not on right on human being or any living object, but experimental this outcomes are this. So, this technique is developing very fast. This results, which of course I will put here references I will include, but these techniques are recent developments, okay, 2015, 16, 17, 18. So, it is going fast, moving towards clinical, right, application if possible, very similar to what we will see with right, OCT etc. in future. Okay. So, with this we complete this part, okay, of applications of absorption.